This video is the second video on electric fields. If you haven't watched the first one, then check it out. The link should be in the description. So this video, we're going to talk about electric force, so force due to an electric field. So we said in the previous video that if we have a negative charge there, a single negative charge, we have a field that looks something like this. The field lines are all pointing at the negative charge because an electric field is dictated by the force on a positive charge. So we're thinking about positive charges. Positive charges are going to be attracted to that negative charge, and so the arrows point inwards. So what dictates the size of that electric force? Well, we said in the previous video that how close the lines were the electric field strength. And so as you can see, the lines get further away as you get further away from the charge, which we would expect. The further away you get from the charge, the weaker the force of attraction. Fair enough. And what you'll actually discover if you think about the area of the remember it's going in 3 dimensions, so the area of the sphere, I suppose, around the sphere of space around that charge, the surface area of that is proportional to the radius of it squared. So our electric force, depends on the inverse square law. So it's proportional to r squared. It's also obviously going to be proportional to the size of this charge. Like, how negative is this charge? Is it just an electron? Is it 10 electrons? Is it 10,000 electrons? So if we have the size of that charge, then we know that the force is going to be dependent on that, and it's also going to be dependent on the size of the charged object that you're putting in there. So if I'm just putting 1 proton in there, then it's going to experience a certain force. But if I put 100 protons or 10,000 protons in there, they're going to experience a larger force. So there's that charge and there's this charge. So the force experienced between 2 charged bodies is proportional to the size, the magnitude of both of those charges, and inversely proportional to the distance between them, squared. Now there's a constant of proportionality in there, which we call Boltzmann's constant, which is denoted by the letter K, so K, Q over R squared. And K basically depends on the material. So we didn't consider this really when it came to gravity, because gravity works through any material, but electric fields are passed through certain materials better than other materials. And so K is equal to 1 over 4 times pi times the permittivity. And K is specifically for air or a vacuum. So in air or a vacuum, we use the permittivity of free space, which is epsilon naught there, which is a value that is in your data book. The value of K is also in your data book. Be careful, there's a couple of Ks in there, so be careful you're using the right one. This one's Coulomb's constant. The permittivity here, this is the permittivity of free space, which is the permittivity. Permittivity means how easily can a field pass through, and this is permittivity of free space, which is air or a vacuum. So this gives us an expression for the electric force experienced by an object of charge Q in an electric field created by a charge of big Q. Now, there's something that's slightly different from the electric force, and that's the electric field strength. Now, the electric field strength is the force per unit charge. Now, you can draw parallels again with gravity, because electric field strength is force per unit charge, and gravitational field strength is force per unit mass. Right, F equals mg, so gravitational field strength is force per unit mass, electric field strength is force per unit charge, which is F over Q. Now, you can therefore derive another expression for that, because if we take this equation and we move this Q over here, then we get an expression for the electric field strength in terms of K and Q. So K big Q over R squared. And all that's saying really is that the electric force is the force experienced by an actual charge in that electric field. But if you don't have a charge, there can still be an electric field. And so, if you don't have a secondary charge to put in the field, if you don't have an object to put in the field, there's still the electric field there, but there's no force experienced. But there would be a force experienced if you put a charge in. So the electric field strength is the force per unit charge. So the electric field strength is basically a slightly more general term for the strength of a field. And so it doesn't take into account the charge of that second object, but it does take into account the charge of the main object creating the field and the permittivity in the form of K and how far away you are from that charge. So those are two equations that are pretty similar, but they have an important difference. The electric field strength is the force per unit charge, and the electric force is the force that's actually experienced by a charge of charge Q. Now just onto some definitions. To elaborate on the definition of electric field strength, we say that the electric field strength is defined as the force per unit charge experienced by a small positive test charge at a point in a field. So it's the force per unit charge experienced by a small positive test charge at a point in a field. The positive is very important. The per unit charge is very important. And it works at any point in a particular electric field. Okay, the test charge is just means that and the small and test charge just means that they have negligible volume. So you don't have to worry about the charge being spread out over a volume. The small and test charge mean that it's got negligible volume. So the electric field strength is the force per unit charge experienced by a small positive test charge at a point in a field. Learn that.